Hello and welcome to the last lesson we're going to have this term before the holiday, and therefore the last lesson of learning before you have your progression exam in a couple of weeks. So we're going to look at concave and convex function, and these are linked to the second derivative of function, which we're used to using when determining whether or not stationary points are a maximum or a minimum. So here we have three functions that have been plotted. We can't see the whole function, it's impossible to see the whole function, but we can certainly see relevant sections of these. We have what looks like a negative quadratic, we have what looks like a positive quadratic, and we have what looks like a positive cubic. And we're going to look at these in turn, and what we're going to do is analyze the gradients. So over on this left function here, you can see that to the left of this maximum point, if we were to find the gradient of any tangent to the left of this point, the gradient would be positive. And then to the right of this stationary point, we can see that the tangents, any tangent that we choose, the gradient would be negative. Okay, so it's sloping down from left to right, whereas over on the left it's going up from left to right. Right in the middle here, we've got a stationary point, which we already know is where dy by dx equals 0. Now what we're interested in here is the behavior of the gradient. So we can say that dy by dx is actually decreasing here. It's going from a positive value through 0 down to a negative value. So our dy by dx is decreasing as we move from left to right. What that means is that our second derivative, and remember the second derivative describes the behavior of the first derivative. It tells you how the first derivative is changing. So the first derivative is changing in the way that it's decreasing. So that means our second derivative is less than or equal to 0. Now this type of function is called a concave function. Or at least we can draw the conclusion that it's concave in the limits that we can see. So concave means that dy by dx is decreasing, which means that the second derivative is less than or equal to 0. The way that you can remember this is it kind of looks like the entrance to a cave. Next, we'll have a look at this positive quadratic, and you can probably already see that we've got the opposite pattern happening. We've got a negative gradient through a 0 gradient across to a positive gradient. So this time we've gone from negative through 0 to positive, which means that our dy by dx this time is increasing. Okay, if we go from a negative value through to a positive value, we've increased. And we can see then, or we can describe that behavior using the second derivative. The second derivative is the rate of change of the first derivative, and the rate of change is greater than or equal to 0 because it's increasing. Now this type of function here we describe as convex. Now you just have to remember concave, and then you'll remember that convex is the other way around. Over on this cubic, we've got a little bit of a mixture of the two. We've got dy by dx is positive over on the left here. We've got dy by dx is negative over on this section, but then over here again, dy by dx switches and becomes positive again. We have our two stationary points, and so we've got a mixture. So what do we do with this mixture? Well, we just say that this function is concave between two x values, okay? So between what looks like x is minus infinity down here somewhere, and somewhere around about here, we know that this function is concave. But at this key point here, it switches, and it becomes convex. So it goes from being this negative gradient through to a positive gradient, whereas before it had gone from positive to negative. So this point here is an absolutely vital point on the graph. And you know this point as a point of inflection. So a point of inflection is where the derivative, dy by dx, the second derivative switches from being less than or equal to 0 for the concave part to greater than or equal to 0 for the convex part. Now let's have a look and see how we use these when we answer questions. First of all, there's just a summary of what we've just described. You do need to know these facts, and hopefully you'll get to the point through working that you won't be able to forget them. But you can pause the video and make a note if you choose to. So this question is asking us to find the interval on which the function is concave. So using function notation, as the question is given in function notation, for a function to be concave, we know that f dash dash x has to be less than or equal to 0. Remember, it's that cave shape that goes gradient positive to gradient negative. So f dash dash x less than or equal to 0. So that's what we're going to find. First of all, we find the first derivative, so we'll differentiate this to get 3x squared plus 4. Then we'll differentiate again to find f dash dash x, our second derivative, which is 6x. Now, if we want to find the interval on which this function is concave, we're just going to solve f dash dash x is less than or equal to 0. So we say 6x is less than or equal to 0. So x is less than or equal to minus 6. Minus 6. X is less than or equal to 0. Never forgive me for dividing 0 by 6 and getting minus 6. Anyway, 0 divided by 6 is 0, so x is less than or equal to 0. So this function is concave where x is less than or equal to 0. Now you might see this written as an interval where minus infinity is your furthest left point and comma 0, again with those rectangular brackets indicating that we're using a limit. So let's have a look at the second question. Okay, that was an example of finding where a function is concave. This time we're looking to see where a function is convex. Now we know that for a convex function, f dash dash x, our second derivative, is greater than or equal to 0. Remember, that's because a convex function looks like this, and it goes from negative through to positive, so it's increasing or greater than or equal to 0. So first of all, we'll find f dash x, and we know how to differentiate these now. So we've got 2e to the 2x plus 2x, and we'll find our second derivative, f dash dash x, which is 4e to the 2x plus 2. So it says show that this function is convex for all real values of x. Now, we're just going to do as we did before, except this time obviously we're using greater than or equal to. So we're going to say 4e to the 2x plus 2 needs to be greater than or equal to 0. Now in order to show that it's convex for all real values of x, we just have to imagine what happens. So no matter what value of x we substitute in here, positive or negative or 0, 4 times e to the power of this number will always be positive. It will always be positive. If x is negative, you might be thinking, all that does is it turns this into a fraction. So you've got 4 divided by e to the power of something, which is still a positive number. And when you add 2 to a positive number, you have a positive number. So we can say that 4e to the 2x is positive for all real values of x. Therefore, 4e to the 2x plus 2 is greater than or equal to 0 for all real values of x. And so we're just making that statement based on some facts that we already know. So we'll go back to this point here, and this was a really key point on this graph. I've shifted it slightly. If I move it back to where I suspect it will be, which is around about here. Remember, this was the point of inflection. Now, at the point of inflection, what's actually happening is the curve goes from concave to convex. Or vice versa. Okay? It is changing, which means that our second derivative d squared y over dx squared has gone from less than or equal to 0 in the first example through to greater than or equal to 0. It's changed sign. Okay, so it's gone from negative to positive. And in the second example, convex to concave, it's gone from greater than or equal to 0 to less than or equal to 0. So again, it's changed sign, except this time it's gone from positive to negative. And that's what a point of inflection does. Now, the other key thing to remember about a point of inflection is, at a point of inflection, d squared y by dx squared is actually equal to 0. And that's what indicates the idea of the sign change. So we have this other curve, x cubed minus 2x squared minus 4x plus 5, and we're being asked to show that it's concave on this interval and convex on this interval, and then we're being asked about a point of inflection. So first things first, let's differentiate to find dy by dx. We get 3x squared minus 4x minus 4. Then the second derivative, d squared y over dx squared, which is going to be 6x minus 4. And let's concentrate on this concave aspect first. So for the function to be concave, 6x minus 4 is going to be less than or equal to 0, which means if we solve, then we get x is less than or equal to 2/3. So for all values of x less than or equal to 2/3, this function is concave. Now you can see that in our interval -2 to 0, these are the x values that we're interested in. -2 through to 0, all of them are less than or equal to 2/3. So in the interval -2, 0, x is always less than or equal to 2/3, therefore is concave. If we're looking at convex, which is what we're also asked to do, then our 6x minus 4 needs to be greater than or equal to 0, which means x is going to be greater than or equal to 2/3. And we can draw the conclusion that in this interval 1, 3, x is always greater than or equal to 2/3, so the function is convex. So now we've been asked to find the coordinates of the point of inflection. Now we've already done a bit of the work for this, but I'm going to explain this in full. To find a point of inflection, we set d squared y over dx squared equal to 0. That's our job. Okay? At every point of inflection, the second derivative is equal to 0. There is something else to this, but we'll get to that in a second. So our second derivative, as we know, is 6x minus 4. We'll make that equal to 0, and that solves to be this key point of x equals 2/3. Now we've seen that. If it's concave for x is less than or equal to 2/3, and convex for greater than or equal to 2/3, then it stands to reason that 2/3 is going to be this point of inflection. But we've made this equal to 0 to show that. Now you might also be asking yourself about this or equal to part here. How can it be concave, convex, and a point of inflection all at the same time? Well, this kind of goes back to what we talked about when we did increasing and decreasing functions. We have the difference between strictly concave and just concave. Strictly concave would be that x is less than 2/3. Concave, we allow the less than or equal to. So here's our presumed point of inflection. Now, finding this x value when d squared y over dx squared equals 0 is part of the process here, but it isn't enough, because there's something interesting about points of inflection. Every single point of inflection has a second derivative of 0. However, not every second derivative of 0 indicates a point of inflection. That relationship doesn't work backwards. So what we've got to show in order to prove that this is a point of inflection is that for x is less than or equal to 2/3, d squared y over dx squared is less than or equal to 0. Okay? Now we've already done that. That's what we did in part A of the question. But had we not done that, we'd have to state this. We'd have to work it out and state it. Also, for x is greater than or equal to 2/3, d squared y over dx squared is greater than or equal to 0. So by doing that, we're showing that there's a change in sign of the second derivative. It goes from negative to positive as we go through the point x equals 2/3. And those two pieces of information together show that we have a point of inflection at the point 2/3. You need to do this second part. So that's it for convex and concave functions. Have a go at the questions and let me know if you need any help. Thanks.